To continue our discussion from Chapter 6, we are now going to look at how z-scores relate to a very important model referred to as the normal model. Z-scores are a combination of taking the mean of a data set and shifting it to 0 and scaling it so that the standard deviation is 1. And we use these z-scores to determine how unusual, very large and very small, z-scores are. And in order to do that, we model the distribution using the normal model. So first let's talk about some notation. So this notation right here represents, if you see n, capital N, parentheses, you know you're talking about the normal model. Then they'll give you two numbers. The first number will automatically be your mean because that is your mu. And the second number will automatically be your standard deviation because that is sigma. So if you see n 5, 2, that means that it's a normal model with a mean of 5 and a standard deviation of 2. Now, your data set that you are working with must be unimodal, meaning one mode, one hump, and symmetric in order to use the normal model. So if you have a data set that is not unimodal and symmetric, you cannot use the normal model. So what the first type of problems we're going to focus on with the normal model, it refers to the 68, 95, 99.7 rule. And what that rule says is in a normal model, 68% of the data fall within one standard deviation of the mean. So your mean is in the very center, as we know. If I go out one standard deviation left and one standard deviation right, that between those two values is 68% of my data. If I go out two standard deviations, so I've already gone out one, if I go out a second standard deviation, left and right, between those two data values lies 95% of my data. So a very good majority of it. If I go out 3 standard deviations, so we've already done 2, there's a third and a third. Notice how thin those little tails are getting on the left and on the right. They're getting thin because we have now established 99.7% of our data is between those two markers. And so we're going to use those 3 cutoffs, 68, 95, 99.7, to answer a variety of questions. And we're going to look at ways of determining some very basic math, but you have to know percentages, 68, 95, 99.7. And the Environmental Protection Agency, the EPA, fuel economy estimates for automobile models tested recently predicted a mean of 24.8 miles per gallon and a standard deviation of 6.2 miles per gallon for highway driving. Assume that a normal model can be applied. That's key. Whenever you hear assume a normal model can apply, that's a good thing. That means that we're able to use our normal model. So what we're going to do first is we're simply going to draw the curve and actually write in all of the values along the x-axis that represent your cutoffs. So draw a flat axis. That's your x-axis. Curve up and curve down. And no, your curves do not have to be perfect because as you can see, mine is not perfect. So in the dead center, if you look at your notes, the very center mark, so I'm going to find the center, which is right there, that was your mean. So our mean is 24.8. So we are going to go out one standard deviation, make sure these are even markings in each direction. So we're going to go up and down one standard deviation, which is 6.2. So 24.8 plus 6.2 moves us up to 31. But 24.8 minus 6.2 moves us down to 18.6. So those are your first cutoffs. So remember, those little lines right there represent 68% 68% of our data. Now we're going to go out again in even marking in each direction. We're going to go out another 6.2. 31 plus 6.2 is 37.2. 18.6 minus 6.2 is 12.4. So now between those two new markings, go up a little higher just so I have some room to write. Between those is 95% of our data. And then I'm going to go out one more marking, left and right. And that's another 6.2, so 37.2 plus 6.2 is 43.4. And 12.4 minus 6.2 is 6.2. And between those two markings is 99.7% of our data. And so now, that's our proper model. So now, in what interval would you expect the central 68% of autos to be found? So 68%, that was my red barrier there. So we would simply say between, because we're reading our graph, 18.6 and 31 miles per gallon. That's how you read the graph. That's how easy that question was. But they are going to get more difficult. So about what percent of autos should get more than 31 miles per gallon? So more than 31, I'm going to draw a quick little demonstration again. This is just a baby version. 31, if that was your mean in the middle, that was the 24.8. 31 was one marking out. So this was your 31. We want to know what percentage of autos should get more than that. More than that is to the right. Well, here's something very important to know about this curve, this normal model. If I technically go on and on and on forever in both directions to the right and to the left, and I count all of the shaded region, I technically have 100%. So when you want to find the area of a shaded region, you need to take the high end of the shaded region minus the low end of the shaded region. Well, this is going forever this way. So the high end of that would be 100. The low end of it, the 31, that was the cutoff for what percentage? That was the cutoff for 68%. So the high was 100 minus the low of 68. We end up with 32. The problem is that's not the answer to that question. And here is why. 31 had a matching partner over here. He had 18.6. That matching partner has a matching wing that goes to this side. Because here's the thing. These graphs are symmetric. That 32 represents both of the wings. So if you only want one wing, all you have to do is divide by 2. And you end up with 16% of automobiles. So to find percentages, you simply take the high percent minus the low percent, but because you only wanted one wing, you have to divide by 2. So let's try a similar question. About what percent of cars should get between 31 and 37.2? Well, if you glance back at your previous slide, again, I'm going to draw a rough sketch. That was your middle. 31 was your first marking to the right, and 37.2 was your second. We want the area between them. So again, your high end of this time is the 37.2. Well, what percentage cutoff, because that is 2 standard deviations, that high is 95%. Minus the low end, 31. That was the cutoff for 68. Whoops, we're not ready to divide yet. We end up with 27. But again, there's a matching wing on the other side. This is only half the graph. So divide it by 2, and you end up with 13.5%. Describe, now we're working backwards, describe the gas mileage of the worst 2.5%. So there's one important keyword there, worst 2.5%. So in terms of a picture, worst is obviously the low end. So the worst 2.5% would be here all the way this way. So that's 2.5%. Well, remember, we always work with a balanced picture. So 2.5% also has to have a mirror on this side. There we go. So that is also 2.5%. So instead of dividing, because think about working backwards, we always had the percentage as the final answer. We always divided by 2 to get that percentage. Well, we're going to multiply by 2 this time because we need both wings included. So that's 5%. Well, we now need to, because we're going all the way to the ends, because remember this one goes this way forever and this one goes this way forever. That means that our high is 100%. We've already used 5%. So that leaves us with 95%. Well, that was one of our magic cutoffs. 95% was cutoff number 2. So if you go back to your original picture, we had the mean in the middle. We had cutoff number 1. These are cutoff number 2. Well, what was the cutoff for the worst, this one here, for 95%? Well, that was 12.4. So describe the gas mileage of the worst 2.5% of cars. Less than 12.4 miles per gallon. So that was definitely your challenge one. The other ones were pretty straightforward. That one was a little more challenging. Let's take a look at another example. As a group, the Dutch are among the tallest people in the world. The average Dutch man is 184 centimeters tall, just over 6 foot, and the average Dutch woman is 170.8 centimeters tall, just over 5'7". If a normal model is appropriate, and the standard deviation for men is about 8 centimeters, what percentage of all men will be over 2 meters tall? So 2 meters, first of all, because everything else is centimeters, we need to take 2 meters and we need to turn it into centimeters. Well, there is 100 centimeters in a meter. So 2 meters is 200 centimeters. So we are going to, because we're talking about what percentage of all Dutch men, we're going to convert this 200 into a z-score using the male data values. So the value we want to convert is 200 minus the male average was 184 divided by the male standard deviation was 8. So 200 minus 184, hit enter, divided by 8 is 2. Now remember, z-scores are 2 standard deviations. Well, 2 standard deviations is that 95% cutoff. But we want to know what percent of all Dutch men are over 2 meters. So if we're thinking about our curve, the mean's in the middle, that was the 184, and we went out 1 standard deviation in each direction. Now we're going out 2. This is where 200 was. So over is all of that. Go in that direction. So just like we did on the previous example, we need to take the high, which going that way forever is 100, minus the low cutoff, which was 95%. That leaves me with 5%. I need to divide that by 2. And what percent of Dutchmen are over 2 centimeters? Or sorry, 2 meters? 2.5%. So that was how we used kind of a combination of everything. We converted it to a z-score, and then we looked at what percentage. Now, let's look at the general rules for working with these normal models. So the first rule, make sure it meets the rule that it's nearly normal condition. I will tell you right now, this is going to be told to you. You should be told somewhere in the problem, it's okay to assume it's normal. I won't give you anything more challenging than that. Make a picture of the model with the given information. The number in the middle, the standard deviations, that's what I mean by the picture. Calculate your necessary z-score, and then find your appropriate percent. You can either use the 68, 95, 99.7% model if you get a z-score of 1, 2, or 3. However, there's a lot of other z-scores out there other than 1, 2, and 3 standard deviations. So you should have picked up with your notes packet a blue sheet that helps us find all other z-scores. Anything other than 1, 2, and 3 is on your blue sheet. So we're going to actually use the blue sheet in just a moment. So just to get you practicing with it and understanding how to use it. So let's talk about this blue sheet that you have. There's 2 sides of it. So if you look at one side, you should see z-scores that are negative. You should see a column of negative numbers. And then on the other side, you should see z-scores that are positive. Okay, so here's what it looks like. You have numbers going down this direction and you have numbers going across this direction. They represent your z-score. The first digits are the down digits. You're going to see things like 0.1, then 0.2, then 0.3, and it keeps going down to 3, I think 2.9. My pen's being dumb. And 3.0, so on and so forth. The numbers going across this way are your third digit. You see something like 0.00, then 0.01, then 0.02. So when you look up these scores, one, you have to make sure you're on the correct side. So this kind of z-score, 1.80, that's a positive z-score. So you should be on the side where the numbers are positive. The first 2 digits, 1.8, tell you to go down to 1.8. So we're looking for 1.8, which is somewhere here. Then, because the third digit is a 0, we just go over to this first spot. So you go down to 1.8, look at that very first spot, and you should see the number 0.9641. Now that number represents your z-score only assuming you shade left. That blue sheet only works when you are shading left. So if you look at my picture, you can obviously see that the shaded in part is to the left of 1.8. So the answer for a z-score of 1.80 would be a percentile of would be 0.9641, or if you wanted to change that to a percentage, move that decimal 2 spots, would be 96.41%. Now, if it's shading to the right, we're going to talk about that here, because let's say, for instance, I was shading over here to the right. If I was shading to the right instead, hypothetical situation, what did I tell you the entire graph adds up to? I told you 100%. And 100% is the number 1. So if this is the side that I need, then whatever number I get off my blue sheet, which was that 0.9641, I simply take 1 minus that answer, and that number would give me the other side, which would be 0.0359, or, move my decimal 2 spots, 3.59%. So if you shade left, you're done when you look it up on the blue sheet. If you shade right, you have to take 1 minus that answer. So now let's apply this to some real problems. Suppose that the birth weights of newborn babies are approximately normal. Notice there's that keyword normal, with a mean of 7.6, so there's your mean, and a standard deviation of 1.3 pounds. So there's all of your information you need. What percent of newborn birth weights are less than 9 pounds? So we were told it was normal. We're going to draw a picture in just a minute. We're going to actually do our z-score first. I find that z-scores are easier done first. So our data value is 9 minus my mean of 7.6 divided by my standard deviation of 1.3. 9 minus 7.6 divided by 1.3. Make sure z-scores, if we were just looking at our blue sheet, it only has 2 digits after the decimal. We always round, and we round appropriately. Remember, 5 and up, you round up. 4 and down, it stays the same. So rounded appropriately, I get 1.08. Now, where is that on my pretty little picture? My pretty little picture, now that we're doing z-scores, 0 is in the middle. 1.08 is over here on the right-hand side. That's my cutoff. Which way am I shading? Well, we want to know what percent of birth weights are less than 9. So less than is left. And we like left. Left means less work. So on your blue sheet, you're going to go to the positive side because 1.08 is positive. You're going to go down to 1.0, and then you're going to go over to the 8 slot. And if you do that, you get 0.8599, and in percentage form, that is 85.99%. So that's your first z-score problem from beginning to end. Let's do some more. What percent of newborn birth weights are more than 7 pounds? So start off the same way. Z-score. 7 is the magic number. Minus. Our mean is 7.6. Divided by our standard deviation of 1.3. Type it in your calculator. Round appropriately. 2 digits after the decimal. Negative 0.46. I put that 0 there for looking it up on the blue sheet. Now let's draw our picture. 0's in the middle. Which way is the negative side? It is over here. Negative 0.46. That is my cutoff. What percent of newborn birth weights are more than? More than means greater than, and greater than means shade to the right. So this is one that I was talking about. We got to do some extra work. So first let's look up on the blue sheet. Negative 0.4, so go to your negative side. Go down to negative 0.4. Go across to the 6 slot, and I get 0.3228. But remember, I said if it shades to the right, you have to take 1 minus, always. That gives me 0.6772, which that is 67.72%. What percent of newborn birth weights are between 6 and 8 pounds? Between is a whole new question. We have 2 data values. Which one do we figure out? The answer is we figure them both out. I always tell people, use your higher one first. So let's start with the higher value of 8. 8 minus 7.6 divided by 1.3. Put that in the calculator. Round appropriately, I get 0.31. Now let's do the lower one. 6 minus 7.6 divided by 1.3. Again, put it in the calculator. Round appropriately, and I get negative 1.23. So what does this look like on the picture, and how do we solve it? Zero's in the middle. The 0.31 is over here to the right. The negative 1.23 is over here to the, the 0.31 is to the right. Negative 1.23 is to the left. But if you look at the keyword, we want to know between them. So what is the trick on a between problem? It's very simple. Look up both numbers on your blue sheet and take the higher minus the lower. So let's start with the higher. Look up, go to your positive side, go down to 0.3, go over to the 1 slot, and I get 0.6217. Flip it over, go to the negative side, go down to negative 1.2, go over to 3, and I get 0.1093. And if I want the amount between them means subtract. So use your calculator, you get 0.5124 or 51.24%. And so we have got a second set of examples just like this. The Virginia Cooperative Association reports that the mean weight of steers, male cows, is 1,152 pounds. Suppose that weights of all such animals can be described with a normal model, there's your key word, with a standard deviation of 84 pounds. So I want you to pause the video and try these 3 problems. I always have people ask me, do I have to draw that picture? If you don't need the picture, you don't have to draw it. But if you make a mistake because you don't draw it, you'll lose points on a test. So you pause the video and you try these 3 problems, and let's see how you do on your own. All right, so let's see how you did on this first one. Z-score. What percent of steers weigh less than 1,000? So 1,000, take away 1152, divided by a standard deviation of 84, left me with an answer of negative 1.81. I had 0 in the middle. Negatives are over here on the left. And this was, as I underlined up here already, a less than problem, so we shade to the left. And so this is an easy one, no extra work. I get 0.0351 on my blue sheet, which is 3.51%. So hopefully you got that first one right. What percent of steers weigh more than, so this is a more than problem, 1350. So my z-score 1350 minus 1152 divided by 84. Round appropriately, I get 2.36. Zero's in the middle. 2.36 is on the right. More than means that we shade to the right. First, look it up on your blue sheet. That got me 0.9909. But because I'm shading to the right, I need to do 1 minus. I get 0.0091, which is 0.91%. Very tiny answer. And finally, what percentage of steers weigh between 2 different values? Big one first. 1,200 minus 1152 divided by 84. I end up with 0.57. 900 minus 1152 divided by 84. I end up with -3. 0 is in the middle. 0.57 is on the right. -3 is way over here on the left. And I'm shading between them. So I look up both of them and I subtract. When you looked up 0.57, you should have gotten 0.7157. When you looked up -3, you should have gotten 0.0013. Subtract those, you should have gotten 0.7144 or 71.44%. And that's the end of this lesson, and we will see you in class.